Well, yes, thank you so much for having me here. Absolutely delighted to speak, and thank you for coming. So what I am going to talk about is actually a method or an idea that was already mentioned a couple of times today. It's essentially a way of providing explanations of algorithmic decisions or decisions made by AI or black box decision-making systems. And I'm going to talk also a bit about the GDPR, which Julie mentioned earlier today. So to start with the GDPR, there we go. Just very quickly, some of the GDPR is great in many senses. It sets a very high standard for privacy and data protection in Europe and in other places where European citizens or customers are served. But there are some limitations to it when it comes to how it constrains AI. And it primarily constrains AI through provisions around automated decision-making. So a couple of the limitations that we see is there are principles that have to do with fairness and transparency, but essentially they're guiding principles, and a number of the provisions that would actually put them into force, or in other words, force a data controller to take a particular action to show, for example, that their decision-making system is fair, are non-binding. And by non-binding, I mean essentially they're in recitals, they're not something that you would actually have to comply with as a data controller, rather than they're more for guidance or suggestions of something that you could do above and beyond the strict letter of the law. Similarly, there is an issue with the right to explanation. Again, a non-binding provision of the law. It was a binding provision in early drafts of the GDPR, but in the final version that was passed, again, it was placed in a recital. And there's been a debate over sort of whether it is actually legally binding, what it would require. And essentially, where we're at is, even if the right existed, even if it was legally binding, what it would actually require a data controller to give you in terms of explanation is not clear. It's not necessarily going to be a right to get an explanation of how a model functions in general or functions at a global level. It may not even be a right to get an explanation of how your particular case was decided, so what the rationale was behind your case. It could just be something very simple where you get essentially a meaningful overview of how the decision-making process occurred, maybe what data types it took into account, what the sources were of those data, but not necessarily a full explanation of the rationale behind the decision. And then finally, all the provisions in the GDPR that have to do with automated decision-making are limited by how automated decision-making is defined. And the way it's defined is that only solely automated processes count, and they must have legal or similarly significant effects. So again, there's ongoing debate about what counts as solely automated versus predominantly automated. If a person makes a decision that is based upon the algorithmic system's recommendation, does that count as solely automated, or is that, again, predominantly and therefore not within the scope of the law? And also, what counts as a legal or significant effect? There's some very interesting guidance that has come out from the Article 29 Working Party in Europe that suggested that actually the definition of what is a significant effect is contextual, and it's going to be vary from case to case. So something that is a significant effect for one person, such as showing gambling advertisements to recovering gambling addict, is not going to be a significant effect for somebody else that does not have a gambling problem. So those are some of the issues that we see with the GDPR. Thank you. But I want to return to this idea of giving explanations of algorithmic decisions. I want to think a bit more about what that would actually mean. And we've had a couple of talks already that have touched on that, so I'll be brief about this. But essentially, some of the questions that have to be asked when you are considering giving an explanation of an algorithmic decision is who's the audience for the explanation. It's not necessarily going to be only the person that was immediately affected by it. Why is explanation being requested? Am I supposed to describe to you how the model functions in general, or should I describe to you the rationale of your particular case? Finally, what information should I provide once I've answered all those other questions? So should I tell you about, again, the data types, the most important features, the general design or method of the system? So some challenges that we see with achieving algorithmic accountability by providing explanations, besides these questions over sort of what information should be given, is there may be reasons that you don't want to give out certain information. For example, you want to protect trade secrets, or the privacy of other people, for example, the people whose data is contained within the training data set. It may be technically unfeasible to provide the sort of explanation that's being requested, which was covered quite well in the previous presentation. And the information that you're giving may not actually be meaningful, or at best not be meaningful, or worse be misleading for the person you're giving it to. So you really have to tailor an explanation to both the recipient's ability to understand and the reason they're requesting the explanation, while at the same time trying to provide some sort of neutral or non-biased, or in other words, information where you're not trying to simply achieve trust or to convince a person that a decision was okay, but rather to give a sort of neutral view of why a decision was reached. So, very quickly, we again had a very good overview of the methods for providing explanations that are available, I'd say, on the technical side or on the computer science side. In general, the way I like to think about them is a lot of it is very similar to scientific modeling. What you're trying to do is create some sort of simplification or approximation of a very complex model. Ideally, you're going to do that in a way where it's human interpretable, so it's something that could be understood by the person that the decision was made about. But there are difficulties, as with scientific modeling, there are difficulties with that approach. The choice of domain is very important. Could end up potentially misleading somebody by essentially giving them an explanation of how a small slice of a model works, and they take that as an indication of how the model functions in general. And this is where this idea of box's maximum comes in, where essentially all models are wrong, but some are actually useful. In order for a scientific model to be useful, in order for a sort of approximation, a local approximation of a black box model to be useful, you have to understand its limitations. You have to understand its resilience. You have to understand where it breaks down. So it doesn't only break down on edge cases, for example, or is it only accurate for a very small subset of decisions. So just to illustrate that point, this is just a very simple example of if we wanted to give a linear approximation of what is also a very simple model. So in this case, the blue line is the model. The red line is the linear approximation of how that model functions. And as you can see from the black lines, the choice of domain, or in other words, the choice of the piece of the model that we want to explain, drastically changes the approximation. And so this is essentially the problem you run into with any sort of local approximation approach to giving explanations of algorithmic decisions, is these limitations have to be explained to the person, and getting across sort of what those limitations are and how they constrain the approximation, how resilient they make it, can be very, very difficult. It can be almost as difficult as trying to explain the model in general. So that's a very, very quick look at what we're doing on the technical side, or on the computer science side. But what do we know about explanations from other fields? So from philosophy, from cognitive science, from social sciences. And there was a very good review done recently by Tim Miller that was essentially looking at empirical evidence from those fields of what makes a good explanation. And a conclusion they came to is that explanations, sort of everyday explanations, the type that the person affected by an algorithmic decision would be interested in, will be three things. They'll be contrastive, which means they will be posed in relation to some other outcome or event that was expected. So in other words, we tend to ask for explanations when the event, the phenomenon, is perceived as abnormal in some way. So I applied for a loan, I did not get the loan. I find that to be abnormal, and I ask for an explanation of why I did not get it. They also need to be selective. And what that means is, for any phenomenon, you can give many, many different explanations. You know, there could be a long causal chain or many different valid explanations of why an event occurred. So for example, why did a wine glass fall to the floor and break? Well, one valid explanation would be because of gravity. Another would be because glass is a softer material than marble that it fell onto. But what I'm actually interested in is to figure out who was responsible for it. So what the explanation, the cause that would actually be useful to me is to know who knocked the table off the glass, or sorry, the glass off the table. And finally, explanations, the last thing was explanations need to be social, which means that there's always an explainer and an explainee. It involves some sort of transfer of information or dialogue between two people. You have to tailor explanations to the expectations and the abilities of both parties. And so if we're looking at explanations as sort of, we're going to create a simplified model, give it to a person, and that's the end of the story, then I think we're going down the wrong path. So the question that I'll end with, and just very quickly cover the method that I mentioned, counterfactual explanations, is essentially how do you bridge the gap between what a lot of the work that's currently going on that is more akin to scientific modeling versus what we know would be sort of a philosophically robust explanation or a good explanation, a good everyday explanation according to those terms. And so the approach I'm describing, it's described in detail in this paper if you're interested in sort of the maths behind it, for example, or seeing some tests that were run with it on a couple of very simple data sets. But the basic idea here is we start from rather than starting from the position of, I'm going to explain to you how a model functions, I want to explain to you how a model behaved in a particular case. And what I actually want to explain to you is, you have some other outcome in mind. So if for example, you applied for a loan, you did not get the loan, the outcome that you wanted was to get the loan. So we're going to tell you, okay, what would have needed to be different about your situation to have gotten the outcome that you wanted? So it's effectively reversing the question, or reversing the purpose of an explanation, which I think actually deals with a lot of the problems that I mentioned previously, in the sense of it immediately makes it sort of much more relevant to the person that's requesting the explanation. And so an example of counterfactual explanation would be this one at the bottom. Is you were denied a loan because your annual income was £30,000. If your income had been £45,000, you would have been offered the loan. So essentially what we're telling you is what would have needed to be different, or what change could have been made to your situation to have gotten the outcome that you wanted. And ideally, we're looking for small possible changes. So it could also be that you would have gotten a loan if your income was £1 million, but that's not necessarily going to be as useful to you to know as the smallest possible change in your income. And so just in comparison to the approximations we were looking at earlier, essentially what we're doing here is saying, okay, where do you want to be, or what outcome did you want? And then we're going to try to explain to you one or more paths to get to that outcome. And a very simple sort of visualization of how this would work. You have this sort of spiky balloon image in the middle, the blue line, that's your decision boundary. That's where you wanted to be, but you weren't. And then you have this red X, which is where you currently are. So what we're basically going to do is start from the red X and expand outwards and get to a point where you actually hit the decision boundary. And as you can see, there are multiple possible locations where you could hit the decision boundary. Essentially what that means is we're able to give you multiple possible explanations of how you could have gotten the outcome that you actually wanted. So for example, with the loan one, it could be that it was based on your income, but it could also be that if you owned one car rather than owning 2 cars, you would have gotten the loan. Or it could be that some change to your income plus some change to the number of cars that you own together would have gotten you the outcome that you wanted. So we're able to not only describe changes to single variables that would have gotten to the preferred outcome, but actually interactions between variables as well, multiple variables. And so I will skip this. This is basically just to say that We think this way of giving explanations is useful in the sense that it can help you understand a bit about how the decision was made, what some of the key features were, maybe able to help you challenge decisions that you disagree with. For example, it could help you find out that the data that a data controller is holding is inaccurate or not up to date, so you challenge the decision on that basis. And again, it gives you some indication of how you can change your behavior to get the decision you want in the future. Now again, it's not a guarantee that that change will lead to it, but it's some indication, assuming the model doesn't change too much and your situation doesn't change substantially either. Okay, so I think we've covered this already. So essentially, the main question that we're asking ourselves, and by us I mean myself, Sandra Doctor, and Chris Russell, who worked on this, is to test this idea in different decision-making contexts. So we're looking at, we're testing it in multiple different types of financial decisions at the moment, and also with image classification. And essentially to start to come up with requirements for what makes a good set of counterfactuals. Because essentially you want to give people counterfactuals that will actually be useful to them, that will ideally be variables that you can change. If I tell you that you would have gotten a loan if you were 10 years younger, that may be interesting, but it may not be terribly useful to you if you actually want to get a loan in the future. So essentially we're looking at what makes a good and sufficient set of counterfactual explanations. So I'll end there.